Eastern Prussia, January 1945. The Third Belarusian Front's artillery barrage had ceased just after 0400 hours, leaving a ringing silence that was quickly filled by the rumble of T-34s and the shouts of advancing infantry. This push, intended to crack the German defenses along the Vistula Lagoon, met an unexpected and brutal counter-response, a flurry of accurate high-velocity fire from positions that should have been overrun. The immediate consequence was a sharp increase in casualties and a frustrating halt to the momentum that had carried them across hundreds of kilometers of Polish plains. The initial reports from the forward companies spoke of a new, heavier class of German anti-tank weapon, far more potent than the ubiquitous Pak-40. Captain Ivan Volkov, a combat engineer attached to the 5th Guards Tank Army, received these dispatches with a growing sense of unease. His role was to assess enemy fortifications and armaments, providing rapid tactical intelligence, and the descriptions coming in suggested something beyond the standard German arsenal. His men, accustomed to the relative simplicity and robust functionality of Soviet designs, were already expressing surprise at the sheer number of unfamiliar components found on captured German equipment, even down to their field radios. As the advance resumed, albeit at a slower pace, the first intact examples of these new German weapons began to appear in the shattered remnants of defensive strongpoints. One such find was a Panzerschreck, a recoilless anti-tank rocket launcher, its distinctive shield and tapered barrel stark against the snow. Volkov's initial inspection noted its formidable appearance, a stark contrast to the more rudimentary Soviet PTRD anti-tank rifle. The German weapon, however, presented an immediate puzzle. Its firing mechanism was not an intuitive lever or hammer, but a complex arrangement of springs, a primer pin, and an electrical contact system, all housed within a meticulously machined casing. The Panzerschreck, officially the Raketenpanzerbuchs 54, was designed for individual infantry use, yet its operational complexity far exceeded that of Soviet equivalents. Volkov's team, after securing several examples, began a detailed examination. They noted the weapon's weight, approximately 9.25 kilograms unloaded, considerably heavier than the Soviet RPG-43 anti-tank grenade, which was a mere 1.2 kilograms. The German rocket, a 88mm fin-stabilized projectile, carried a shaped charge capable of penetrating 160 millimeters of armor, a significant threat to the T-34's frontal glacis. However, the weapon required a two-man crew for optimal operation, one to load and one to fire, and its delicate electrical ignition system was highly susceptible to moisture and cold, common conditions on the Eastern Front. Further analysis revealed the intricate manufacturing processes involved. The rocket motor casing was drawn from high-grade steel, precisely machined to ensure a perfect fit with the warhead and propellant charge. The propellant itself, a smokeless diglycol powder, was carefully calibrated for consistent thrust. The firing mechanism's spring-loaded contact points and insulated wiring required a level of precision engineering that spoke to an industrial base focused on meticulous detail rather than mass-produced simplicity. This was a stark contrast to Soviet doctrine, which prioritized ruggedness and ease of field maintenance, often at the expense of absolute technical sophistication. The implications for Soviet forces were immediate and tactical. While the Panzerschreck offered superior penetration against heavier tanks, its operational demands and susceptibility to environmental factors meant that a captured weapon was not easily integrated into the Soviet infantry's fighting doctrine. A Red Army soldier, trained on the robust and straightforward Mosin-Nagant rifle or the PTRD, found the German weapons assembly and maintenance procedures daringly intricate. The requirement for specialized ammunition, an 88mm rocket, further complicated its battlefield utility. Soviet logistics were not equipped to supply such a specific and non-standard munition. The initial impression of a powerful, advanced weapon quickly gave way to the realization that its very sophistication made it a liability in the hands of an unprepared, non-specialized force. The initial skirmishes yielded a haphazard collection of German armaments. Soviet infantry, pushing through shattered lines and overrun positions, would often find themselves amidst the detritus of a retreating Wehrmacht, their eyes drawn to the distinctive profiles of enemy weapons. A captured Kar-98K rifle, its blued steel barrel still warm for recent firing, represented a tangible victory, a trophy of the immediate engagement. These early acquisitions were largely individual efforts, soldiers picking up what they could use, or what seemed superior to their own, often worn-out Mosin-Nagants. As the Red Army advanced deeper into enemy territory, the scale of capture shifted from individual weapons to entire caches. Supply depots, hastily abandoned or poorly defended, presented a far richer haul. A unit diary from the 21st Guards Rifle Division, dated September 1943, records the discovery of a warehouse near Poltava containing approximately 300 Mauser rifles, 50 MP-40 submachine guns, and several crates of Panzerfausts. This was no longer about personal acquisition, but about integrating enemy materiel into the broader logistical chain, a process that immediately exposed the inherent differences in design philosophy. The German MP-40, a ubiquitous sight on the Eastern Front, exemplified this divergence. Its construction, primarily stamped steel and bakelite, allowed for rapid mass production, a testament to wartime industrial pragmatism. Soviet ordnance specialists, examining captured samples, noted the clever use of a telescoping return spring that encased the bolt, reducing overall length and simplifying field stripping. However, this same design, while robust, demanded a specific grade of steel and a precision in stamping that Soviet factories, geared for simpler, more robust designs, often struggled to replicate or even fully appreciate in their own production lines. The MP-40's relatively low cyclic rate of fire, approximately 500 rounds per minute, was a deliberate choice for controllability, a contrast to the Soviet PPSH-41's often frantic 900 rounds per minute, reflecting differing tactical doctrines regarding suppressive fire versus aimed bursts. The MG-34 and later the MG-42 machine guns presented an even greater challenge. The MG-34, a marvel of precision engineering, featured complex milled components and a quick-change barrel system that was both innovative and, for Soviet mechanics, intimidating. Its intricate feed mechanism, designed to function reliably with both belt and drum magazines, required meticulous maintenance and specific lubrication, a stark contrast to the comparatively crude, yet highly resilient, Soviet DP-28 light machine gun. Production logs indicate that a single MG-34 required 49 kilograms of steel and 150 man-hours to produce, figures that underscored its material and labor-intensive nature, making it a difficult weapon to field in vast numbers, even for the Germans. The Panzerfaust, a recoilless anti-tank weapon, initially seemed a godsend, offering a potent counter to German armor. Its simplicity, a single-shot tube with a shaped charge warhead, belied a sophisticated understanding of explosive physics. However, Soviet troops quickly discovered its limitations, a very short effective range, typically 30 meters for the Panzerfaust 30, and a single-use design that necessitated a constant supply chain. The German emphasis on disposable, specialized anti-tank weapons contrasted sharply with Soviet doctrine, which prioritized multi-role anti-tank rifles and towed artillery, reflecting different resource allocations and strategic priorities. Captured optical equipment, particularly binoculars and rifle scopes, further highlighted the German commitment to precision. Zeiss optics, renowned for their clarity and robust construction, were frequently recovered. Soviet analysis reports often detailed the superior light transmission and magnification of these lenses, noting the complex grinding and coating processes involved. While Soviet optics were functional, they rarely matched the German standard, a disparity that affected long-range engagement capabilities and reconnaissance efforts. This qualitative difference, though not always immediately apparent on the chaotic battlefield, contributed to a broader perception of German technological superiority, even as the Red Army's sheer numerical advantage often negated it. The meticulous assembly and calibration required for these instruments made them difficult to repair or replicate without specialized facilities and skilled technicians, resources often scarce behind the rapidly moving Soviet front lines. Winter 1942, Leningrad Front. The initial euphoria of capturing intact German weaponry quickly gave way to a more sober reality as the Red Army's ordnance experts and engineers began their meticulous examination. A Panzer III OSF-J, its tracks frozen solid to the scarred earth, represented a significant prize, yet its internal mechanisms presented an immediate challenge. Soviet tank crews, accustomed to the relatively straightforward operation of their T-34s, found the German tank's control layout and intricate electrical systems bewildering, a stark contrast to the robust simplicity that defined their own designs. The captured MP-40 submachine gun, a ubiquitous symbol of the Wehrmacht, underwent extensive scrutiny at the Tula Arms plant. Its stamped steel construction, a marvel of wartime efficiency, was noted, but the complex multi-part bolt assembly and the meticulous tolerances required for its reliable function were points of concern. Soviet production logs from 1942 indicate that the average time to machine a single PPSH-41 receiver was 7.2 hours, a figure dwarfed by the estimated 18 hours required to produce an MP-40 receiver with comparable precision, based on reverse engineering trials. This disparity highlighted a fundamental difference in manufacturing philosophies, where German engineering prioritized sophisticated componentry, even at the expense of mass production speed. Artillery pieces, particularly the formidable 8.8 centimeter Flak 36, presented their own set of complexities. Soviet gun crews, trained on the mechanically simpler 76mm divisional guns, struggled with the Flak 36's advanced optical sights and intricate elevation and traverse mechanisms, which incorporated hydraulic dampeners and complex gearing. Interrogation files from captured German artillery officers frequently detailed extensive training regimens, sometimes exceeding 6 months, dedicated solely to the mastery of these sophisticated systems, a stark contrast to the Red Army's accelerated 3-month training cycle for its own gunners. The Flak 36's multi-purpose design, functioning effectively as both an anti-aircraft and anti-tank weapon, demanded a level of operational flexibility and technical understanding that was not inherent in Soviet doctrine or equipment. The MG-34 machine gun, lauded for its versatility and high rate of fire, revealed a labyrinthine internal structure upon disassembly. Its quick-change barrel system, while innovative, required a precise sequence of actions and careful handling, a vulnerability in the brutal conditions of the Eastern Front, where speed and durability were paramount. Damage reports from the 3rd Shock Army in early 1943 documented instances where captured MG-34s, deployed by Soviet units, suffered frequent stoppages due to improper barrel changes or insufficient lubrication. Issues rarely encountered with the more forgiving DP-27 light machine gun. The German weapon's finely machined components, while contributing to its accuracy, also made it highly susceptible to the pervasive mud and dust of the Russian steppes. Even seemingly minor items, such as German field radios, presented a challenge. The Fu-G5, a standard tank radio, utilized a complex array of vacuum tubes and crystal oscillators. Requiring precise tuning and delicate handling, Soviet radio operators, accustomed to the more robust and simpler A7 radio, found the few G5's multi-band capabilities and sensitive controls difficult to master under combat stress. A technical evaluation report from the NII-20 Research Institute in late 1942 noted the superior signal clarity of the German sets, but concluded that their operational complexity and reliance on specialized components made them impractical for widespread Red Army adoption without significant re-engineering and extensive training. The inherent precision of German design, while technically superior, often came at the cost of battlefield resilience and ease of maintenance, a trade-off the Red Army was increasingly unwilling to make. The captured MP-40, a ubiquitous sight in German hands, became a subject of intense scrutiny in Soviet ordnance workshops. Its stamped sheet metal construction initially suggested a simplicity that belied the internal complexity, a stark contrast to the milled receivers and simpler trigger groups common in Soviet submachine guns like the PPSH-41. Soviet engineers, accustomed to designing for rapid mass production under duress, sought to understand how the Germans achieved such a high rate of fire and reliability with seemingly less robust external components. Disassembly revealed a carefully engineered system of interlocking parts designed for both efficient assembly and precise function. The bolt, a relatively heavy piece, incorporated a telescoping return spring guide that also served as a dust cover, a clever integration of multiple functions into a single component. This design reduced the overall length of the weapon when the bolt was in its forward position, contributing to its compact profile, but it also introduced a level of manufacturing precision for the spring and its guide that exceeded typical Soviet tolerances for such a high-volume weapon. The trigger mechanism, while seemingly straightforward, employed a series of levers and pins that provided a crisp break and a positive reset. Features often sacrificed in simpler designs for the sake of speed. Each component, from the sear to the disconnector, was machined to tight specifications, ensuring consistent operation even under adverse conditions. This precision, while beneficial for the individual weapon's performance, demanded specialized tooling and skilled labor, factors that limited the rate at which such mechanisms could be produced on a truly massive scale. Examination of the STG-44, a weapon encountered with increasing frequency, further highlighted this disparity. Its gas-operated system, a relatively new concept for a standard infantry rifle, featured a long-stroke piston and a tilting bolt, mechanisms that required careful alignment and robust materials to withstand the pressures of the intermediate cartridge. The gas block itself was a multi-part assembly, precisely bored and fitted to ensure consistent gas flow. A level of detail that would have been deemed excessive for the Red Army's primary rifle, the Mosin-Nagant, which relied on a much simpler, robust bolt-action design. The manufacturing process for these German components often involved multiple stages of machining and heat treatment, as evidenced by the varying surface finishes and hardness levels observed. For instance, the locking lugs of the STG-44 bolt showed evidence of case hardening, a process that significantly increased wear resistance but added considerable time and energy to the production cycle. Soviet analysis of captured production facilities confirmed that German factories maintained a higher proportion of skilled machinists and specialized equipment per unit output compared to their Soviet counterparts, where raw material volume and simplified designs were prioritized. This intricate internal engineering, while yielding weapons of high individual quality and performance, presented a significant hurdle for Soviet forces seeking to integrate captured arms. The lack of readily available spare parts, coupled with the specialized knowledge required for field maintenance and repair, meant that many captured weapons, once a component failed or wore out, became effectively inoperable. The complexity, designed for German industrial strengths, inadvertently became a liability when these weapons fell into hands accustomed to a different philosophy of war production. The captured materiel, meticulously catalogued and transported eastward, eventually found its way into the analytical workshops and proving grounds of Soviet design bureaus. Engineers and ordnance specialists, accustomed to the robust simplicity of their own designs, began the intricate process of disassembly and examination. A Tiger I tank, its formidable 88mm KWK-36 L56 cannon, still smeared with the grime of battle, presented an immediate challenge. Its fire control system, incorporating a Carl Zeiss TZF-9B binocular periscopic sight with impressive magnification and an elaborate range-finding reticle, far surpassed the comparatively basic optics found in a T-34. The precision ground lenses, the intricate mechanical linkages for elevation and traverse, and the robust housing itself spoke to a manufacturing philosophy prioritizing optical clarity and durability even at significant cost. Disassembly of the Tiger's Maybach HL230 P45 engine, a V12 gasoline unit producing 700 horsepower, revealed a level of internal machining and component tolerance that struck the Soviet engineers. The use of roller bearings in critical areas, the complex oil circulation system, and the meticulous balance of the crankshaft were all indicative of a high-precision engineering approach. This contrasted sharply with the Soviet emphasis on readily manufacturable, often less refined, components that could be produced in vast quantities. Production logs from the Uralmash and TCTZ factories, detailing the manufacture of V2 diesel engines for T-34s, showed a clear preference for robust, easily replicated designs, even if it meant a slight compromise in power-to-weight ratios or fuel efficiency. The Panther tank, with its sloped armor and formidable KWK-42 L70 cannon, further highlighted this disparity. Its interleaved road wheel system, while offering superior weight distribution and a smoother ride, was a nightmare for field maintenance. Changing an inner road wheel required the removal of multiple outer wheels, a time-consuming process under fire. Soviet tank doctrine, born of vast distances and often rudimentary repair facilities, favored simpler, more accessible suspension systems, even if they transmitted more shock to the crew. The German design, while technically advanced, seemed to prioritize optimal performance over battlefield practicality in a protracted, resource-intensive conflict. Small arms, too, told a similar story. The Sturmgewehr 44, a revolutionary weapon, showcased advanced stamping techniques and a gas-operated system that allowed for selective fire. Its 7.92 by 33mm Kurz cartridge, an intermediate round, represented a sophisticated understanding of infantry engagement ranges. However, the complexity of its manufacturing process, involving numerous stamped and welded parts, contrasted with the Soviet PPSH-41 submachine gun, which, despite its high rate of fire, was a much simpler design, often produced with less refined tolerances and fewer intricate components. Soviet production figures for 1944 indicated over 1.6 million PPSH-41s manufactured, a volume achieved through design simplicity and mass production techniques. Even seemingly minor components revealed this divergence. German radios like the Fuji 5 were often modular, robust, and offered excellent clarity, but their internal circuitry was intricate, employing numerous vacuum tubes and precision-wound coils. Soviet radios, while functional, were typically simpler, sometimes sacrificing range or clarity for ease of manufacture and repair in the field. The inherent complexity of the German designs, while yielding superior individual performance in many cases, often translated into higher material costs, longer production times, and a greater demand for skilled labor, resources that were increasingly scarce in the Third Reich as the war dragged on. This meticulous engineering, while a testament to German industrial prowess, was becoming an albatross in the face of the Soviet Union's relentless, simplified mass production. The logistical reports from the Central Artillery Directorate in late 1943 began to paint a stark picture of captured German material. While initial enthusiasm had led to the forward deployment of hundreds of captured machine guns and a scattering of heavier anti-tank pieces, the true cost of their integration was becoming apparent. The German emphasis on specialized alloys and precision machining, while yielding superior individual components, created a systemic vulnerability when these items fell into Soviet hands. A detailed analysis of captured MG-34 and MG-42 machine guns revealed tolerances measured in hundredths of a millimeter, demanding high-grade tool steel and meticulous calibration. Soviet small arms production, geared for mass output, relied on simpler designs, looser tolerances, and more readily available materials like stamped steel and less refined alloys. A typical Soviet PPSH-41 submachine gun could be manufactured in approximately 7.3 man-hours, a figure dwarfed by the estimated 49 man-hours required for a single MG-42, factoring in the specialized tooling and skilled labor. The disparity extended beyond small arms. German optical equipment, particularly for artillery and anti-tank guns, employed multi-coated lenses and nitrogen-purged housings, requiring facilities and expertise simply not present in many Soviet repair depots. Damage reports indicated that even minor impacts could render these complex sites unusable, and replacement parts were non-existent. A captured PaK-40 anti-tank gun, while formidable, became a static obstacle if its primary aiming mechanism was compromised, a common occurrence in the brutal close-quarters fighting on the Eastern Front. Production logs from Soviet ordnance factories demonstrated a clear preference for designs that prioritized ease of manufacture and field repair. The T-34 tank, for instance, utilized a robust, if sometimes crude, construction that allowed for rapid assembly and simplified maintenance under combat conditions. German tanks, by contrast, with their intricate transmissions, interleaved road wheels, and sophisticated fire control systems, presented a maintenance nightmare. A single broken torsion bar on a Panzer V Panther could necessitate hours of specialized work, often requiring a dedicated recovery vehicle and trained mechanics, luxuries frequently unavailable to frontline Soviet units. The inherent complexity of German engineering thus became a double-edged sword. While it conferred a tactical advantage in the hands of its intended operators, it simultaneously limited its utility as a captured asset. The Soviet industrial machine, designed for resilience and volume, found itself ill-equipped to either replicate or sustainably maintain these intricate foreign systems. The arithmetic of war for the Soviets favored simplicity and abundance over individual technological superiority. Eastern Front, October 1943. The initial euphoria of capturing German armaments had long since faded, replaced by the grim realities of battlefield logistics and maintenance. A formal report, compiled from frontline observations, technical evaluations at ordnance depots, and feedback from training units, began to circulate through the Stavka. Its purpose was to synthesize the disparate experiences of Soviet troops with captured German small arms and crew-served weapons, providing a definitive assessment for future policy. The report detailed the widespread capture of German weaponry, noting that in some offensives, particularly during the summer and autumn of 1943, up to 15% of infantry small arms found in Soviet hands were of German manufacture. This figure, derived from quartermaster inventories, reflected both the intensity of the fighting and the opportunistic nature of Soviet resupply. However, the document quickly pivoted from quantity to quality, or rather, to the practical implications of that quality. Technical examination of the Sturmgewehr 44, for instance, highlighted its advanced stamped steel construction and intermediate cartridge, acknowledging its revolutionary design. Engineers noted the precision milling of critical components and the careful heat treatment of bolt carriers, contributing to its robust yet lightweight profile. However, the report underscored the weapon's reliance on specialized tooling for manufacture and its susceptibility to field stripping errors by inadequately trained personnel, leading to frequent stoppages. The NG-42 machine gun received similar scrutiny. Its astonishing cyclic rate of 1,200 rounds per minute, a figure confirmed by range tests, was recognized as a significant tactical advantage in suppressing enemy positions. Yet this very rate placed immense strain on its barrel, necessitating frequent changes, a process complicated by the German barrel change mechanism, which, while efficient, required specific training and often specialized gloves due to heat. Soviet machine gun crews, accustomed to the simpler, more robust DP-27, found the MG-42's maintenance demanding under fire. A quantitative comparison of parts interchangeability revealed a stark contrast. The Soviet approach, exemplified by the Mosin-Nagant rifle or the PPSH-41 submachine gun, prioritized broad interchangeability of components, often at the expense of minute precision, allowing for easier field repairs with scavenged parts. German weapons, conversely, exhibited a higher degree of bespoke fitting and tighter tolerances, making battlefield cannibalization less effective and demanding a more sophisticated supply chain for spare parts. Unit diaries frequently recorded instances where a seemingly minor breakage rendered an otherwise functional German weapon inoperable for extended periods. The strategic implication was clear. While individual German weapons often represented a pinnacle of contemporary small arms design, their complexity and specialized maintenance requirements rendered them unsuitable for widespread institutional adoption by the Red Army. The report concluded that the logistical burden of maintaining a dual-standard armory, particularly with weapons requiring unique ammunition and intricate spare parts, far outweighed the tactical advantages offered by their superior individual performance. The Soviet industrial model, geared towards mass production of simple, robust, and easily maintained weapons, stood in direct opposition to the German philosophy of precision engineering, creating an insurmountable chasm in practical application. Recommendation: continued use of captured weapons as available, but no formal integration into standard issue or large-scale rearmament. The winter of 1944 brought with it a renewed appreciation for the brutal simplicity of Soviet war material, a stark contrast to the intricate German designs now frequently encountered and occasionally appropriated. Damage reports from the Third Belarusian Front, compiled in January 1945, detailed the increasing maintenance burden associated with captured Panzerfaust 60s. While effective in single engagements, their single-shot nature and reliance on specific propellant charges meant a constant demand for resupply of a non-standardized munition type, a logistical nightmare for units operating deep behind enemy lines. Soviet ordnance officers, tasked with assessing the feasibility of integrating captured German small arms, consistently noted the superior finish and tighter tolerances of weapons like the MP-40 submachine gun. However, this precision came at a cost. Field repair logs from the First Ukrainian Front, dating from February 1945, recorded an average of 1.7 hours spent on routine cleaning and minor adjustments for a captured MP-40, compared to 0.5 hours for a PPSH-41. The German weapon's complex recoil spring assembly and multi-part trigger mechanism were particularly susceptible to fouling from the ubiquitous battlefield dust and mud, often requiring specialized tools not present in standard Soviet infantry kits. Production logs from the Tula arms plant for the first quarter of 1945 showed a sustained output of 3,500 PPSH-41 submachine guns per day, a rate achieved through simplified manufacturing processes and robust design. This contrasted sharply with intelligence estimates derived from captured German factory schematics, indicating that the production of an MP40 required approximately 18 man-hours of skilled labor, utilizing precision milling and stamping. The PPSH-41, by comparison, relied heavily on less precise, high-speed stamping and welding, reducing its per-unit labor requirement to an estimated 7 man-hours, making it inherently more adaptable to mass production under wartime pressures. The philosophical divide between the two approaches became increasingly evident as the war progressed. German engineering, rooted in a tradition of meticulous craftsmanship and incremental improvement, prioritized individual weapon performance and mechanical sophistication. Soviet design, conversely, embraced a doctrine of brute force efficacy, emphasizing ease of manufacture, reliability under adverse conditions, and the capacity for rapid, large-scale deployment. This divergence was not merely a matter of industrial capacity, but a fundamental difference in strategic outlook, where quantity and resilience often trumped individual precision. The logistical challenges of maintaining a diverse arsenal of captured German weapons ultimately reinforced the Soviet General Staff's commitment to its own standardized, albeit less refined, equipment. Interrogation files of captured German logistics officers, compiled by Smersh in March 1945, frequently highlighted the German Army's struggle with spare part shortages for their own complex machinery, a problem exacerbated by Allied bombing campaigns. The Soviet system, with its fewer component types and greater interchangeability, proved more resilient to the disruptions of total war, a lesson learned through the crucible of attrition. The sheer volume of Soviet production, exemplified by the 6.1 million Mosin Nagant rifles manufactured between 1941 and 1945, dwarfed any German equivalent for a single small arm type. This numerical superiority, born from a design philosophy prioritizing simplicity and mass, became an undeniable force multiplier. The captured German weapons, though individual